Hi everyone, this is Team Jojo, and the topic of our project is fast transfer learning for GAN style transfer. First, we have a GAN network trained to perform style transfer from real image to style A. Then we want to perform transfer learning to train a new network to transfer style from real image to style B. One common way of transfer learning is fine-tuning. It uses pre-trained weights as initialization and train on the new dataset, but it is just a better initialization and does nothing else. Can we improve it by considering the model size, data, and training time? Thus, our task is first to re-implement the cartoon GAN model provided in the paper, then perform effective transfer learning from Hayo style, which is style A, to Iraqi style, which is style B, using this network. And the goal is to achieve faster learning with less trainable parameters. To achieve our goal, we first try naive fine-tuning techniques for our cartoon GAN model as a baseline reference. We use the model trained on Hayo style images as the initialization and train it on our Iraqi style dataset. Beyond that, we introduce meta-transfer learning. We will call it MTL for short. MTL was previously used on classification tasks, but never used in GAN style transfer. To fit the problem well, we separate this method into two parts, scaling and shifting and generator decomposition. Let's talk about scaling and shifting. The first rule is the pre-trained weight, and the second rule is the new weights. In baseline, all the weights need to be trained. In MTL, we can assume that the new weights are obtained by scaling and shifting the pre-trained weights. This is the scaling, and this is shifting. The parameters in the original model are frozen, and only the scaling and shifting parameters are being updated during the training process. This method significantly reduces the learnable parameters and increases the training speed. The second part is decomposing the generator. This is the general structure of our generator. Intuitively, we can divide it into encoder part and decoder part. The encoder should be able to extract low-level features of given images, like edges, points, and so on. So we expect it to keep almost the same given image in different styles. In order to further investigate the division between encoder and decoder, we have visualized the output of each convolutional layers of 4 different animation styles generated from same real image input. This is the real image. As you can see, compared to deeper layers, the output of the shallow layer has a similar result across different style images, which means it extracts style invariant features, so we choose it as the end of the encoder. This is the overall result of our project. We have largely reduced the number of parameters by 10 times and also make our model faster to train. Here are some results from different styles. From the image, you can see a clear difference between the real image, Hayo style images, and Iraqi style images. Hayo is more red, Iraqi image has sharper edges. These two are from the baseline and MTL with fixed encoder. Here is the result for comparing baseline and MTLs, which is our approach. They are all trained on Iraqi style. MTL with fixed encoder produces similar quality as baseline. Although baseline preserves more details, for example, the cheek here, here, and here. Also, MTL with fixed encoder produces better results than naive MTLs, which is the one without the fixed encoder. The naive MTL is more red, which is more like the Hayo style. Here are some field examples. The scaling and shifting restriction of weights seem to worsen the GAN stability and cause mode collapse and artifacts. Here is an example of mode collapse. The generator sometimes turns the image into entire black. Here are also some examples of artifacts like the overlay yellow and changing color. To wrap up, MTL is a more effective transfer learning method on GAN style transfer network with less trainable parameters and faster training, but it worsens some of the GAN's problems like the mode collapse and artifacts. This is our presentation. Thank you for watching.